So my name's Rich Park. I'm an APL programmer and I do outreach and training for Dialogue Limited. In this talk, I'm going to be introducing the APL language in the context of a problem that I think has, the solution for it, the reasoning through the solution, the logic behind it, and the thought process for the solution, I think really beautifully translates into APL. So, if you're brand new to APL in that you've never really used it before, hopefully I'm doing this at a pace and going through things in a way that you'll be able to follow along with nicely. Even if you have done some APL before, you might pick up one or two new things, or even as an experienced APLer, maybe you'll enjoy seeing this example, because I think it really shows off quite nicely both the use of APL as a notation, as well as the array processing capabilities. So to start with, I'm going to introduce some of the very basics. Of course, if you've even heard of APL and you've never done it before, like some of you, then it's likely, you must know about the symbols, right? One of the key features of APL is that the core primitives, the basic building blocks of the language, are represented by symbols, where they might be represented by keywords in some other languages. And obviously at first, if you've got all of these here, perhaps that could be a bit daunting, how we're going to learn all of these. But of course the answer is one step at a time. And, this is no exception. I'm only going to be explicitly showing quite a small subset of the language as we go through, and hopefully make it quite digestible. So yes, there are symbols, but sometimes, you'll see some expressions in some piece of APL media, and you might think, well, that looks quite complicated to do. But actually, the syntax of APL is remarkably simple. We really just have, at the basic level, we have two argument functions, infix, so they go between the arguments, and we call these dyadic functions. So one example is multiplication, and another is subtraction. And then on the other hand, we have our one argument functions. We call these monadic functions. They go before the argument, even if that argument is itself a whole array of elements. We say this just takes one argument. So this here is negation. We're going to get the negative or negate all the numbers in this list. And another example here is iota, the index generator, says get me the first 7 integers. So then how do you piece these things together? Many people say and hear that APL goes from right to left. I find it slightly more useful to think of it as functions, especially dyadic functions, have a long right scope and a short left scope. So here, iota 7, we have the literal number 7, and then we get the first 7 integers. If we want to multiply those by 2, we do 2 times iota 7. That times is taking the result of everything to its right as its right argument, and the thing to its immediate left as its left argument. So we multiply those numbers by 2, and we can do -1 plus this, or subtract 1, to get the first 7 odd integers. And here note the short left scope, the long right scope, the times is taking the value to its immediate left as its left argument, but the result of everything to its right as its right argument. And yes, you typically, when you're working through a problem, you'll build up solutions from right to left in this way, adding pieces to the left as you go along quite often. Eventually, you can become comfortable enough with certain patterns and idioms that you do just spell them out. You type from left to right, and you're sort of confident you know that this is going to do what you expect. At the end of the day, the computer sees this expression, and yes, it evaluates it from the right. So it looks for a value or a function, well, whatever the symbol is, but in this example, we have a value, a literal number 7, and that just gets evaluated as a 7. Then we see this function. Oops, go back. This iota, and we have to ask, is this being called monadically or dyadically? Well, if we look to the left, we see another function. So that's not a value, so that means this is called monadically. So then that evaluates to the first 7 integers. Looking left again, we see this times, look to its left, and there is a value here. So that means this multiplication, or this cross symbol, is dyadic multiplication. So we'll do 2 times our list of numbers, and so on and so forth. The last piece of syntax I want to show you explicitly before we look at the problem is operators. So here's how we can sum a list. Here's a list of numbers. If we want to add them all up, we can put a plus between each of those. That's fine. APL will go through this as it does and get our sum 17. But there's a slightly nicer way to do this and a way that scales better in code, and that's to use the reduction operator. So this forward slash goes together with our function, the plus, and forms a new function, the sort of plus reduction, to sum up a list. But it has a similar effect to just putting the pluses in between each element. But the fact that we've explicitly got the function written here with our operator suggests that we could put something else instead. And indeed we can. If we change this plus to a times, we get the times reduction, the product of our list. Or we put an up style, we can find the maximum value in our list, or the minimum value. And then the last operator, the last thing I want to show before the problem, and it's particularly useful in my example that I'm going to show you, is the outer product. So this is the concept of applying a function between all combinations of elements from both arguments. So we're going to multiply the numbers 1, 2, and 3. We're going to multiply those with all of the numbers 1 to 5. And when we do all of these multiplications, the result we get is a table, otherwise known as a matrix. It is a 2-dimensional array with 3 rows and 5 columns, because we have 3 elements on the left and 5 elements on the right. And once again, having that function explicitly written with our operator suggests we could put something else. So yeah, we could add all those numbers, or sum them up, well, sum them together, or find which numbers are equal to which other numbers in particular positions, or greater than or equal to. And logical comparison like this in APL is considered Boolean comparison, but Booleans in APL are just 1s and 0s. They're just numbers like any other. So this means we can do quite useful things like adding them up. So the plus slash, we were summing a list before. Now we have a matrix. We're going to sum each row of the matrix. So in the first row there's 1, 1. Second row there's 2. The third row is 3. And we get back a 3-element list. Alternatively, if we use, instead of a slash with a bar, which is another symbol, then we can get the sums down the columns. So 3, 2, 1, 0, 0. And that's all the basic concepts I want to prime your brain with, let's take a look at our example. So this is a problem. This is part of a problem that comes from the 2022 APL problem solving competition. And quite appropriately, it's about online user meetings. So Dialogue every year has a user meeting in the autumn. Usually it's in person. Users and Dialogue staff get together, present interesting topics, and get to meet and discuss various things to do with Dialogue and APL. Now in 2020 and 2021, these were held online, much like this event here, with people registering beforehand and then coming to the sort of Zoom webinar to watch the presentations. And afterwards, we got a table with some data about attendance. So here's a snapshot of something like what that looks like. We have, anonymized, well, random made-up names in the attendee column. And also, it's one name per attendee. People don't share names. That's the same Jaslyn Chapman there. And we have a column with the join time. So that's when someone connects to the meeting, the time that they joined, and the leave time. And the same person can join and leave multiple times throughout the sessions. In fact, it's slightly interesting here that Jaslyn seems to have left and joined in the same minute. Perhaps there was a connection issue, I don't know. And also we have the schedule, obviously, because we make the schedule ahead of time. So we've got some session IDs that I don't really use. We have the titles of each session or each talk, the start time and the end time. And so the question is, who attended online user meetings? What we want to find out is, for each person who came, which sessions did they come to see? Which sessions did they attend? Or more specifically, our function that we're going to write, so the code we're going to write, is going to return a Boolean matrix. So this is a two-dimensional array of ones and zeros. Every row is going to be a person who came to the user meeting, and every column is going to be one of our sessions. And then a 1 means that a person was present at the user meeting for at least half of the duration of that particular session. So here I've added the column header as the session titles and the row header as the attendee names. But what we're really interested in and what we're going to compute is this array of ones and zeros, indicating who turned up when or for what. So now we need to think a bit about the data we have and how we're going to use that to get the answer we want. Here I've marked on the timeline each of our sessions, but I can mark the duration of a specific session with a line like this. So we have the duration, the start and end times of each session, and we have these connections when someone joins and leaves, which I've got as a dashed line here. And what we need to look at, what we're interested in, is the overlap of these two lines. Because that means that a person was present during that session. How are we going to compute this? Let's make it a bit more concrete. Well, we can assign variable names for the data that we do have. So the session start time, I'll call that start. The session end time, I'll call that the end. When a person joins for a particular connection, I'll call that join. And if they disconnect, if they leave, I'll call that leave. And so our overlap here is demarcated, it's defined by the later time of the start and the join, start and the join times. And that's just the max between start and join. And the upper bound here of our overlap is the older time, the lower time, the minimum between the end and the leave times. And that overlap duration then is simply the difference between these two. And that's really the core of the solution. That's the basic thing. Everything else is just sort of incidental to the way the data is and having multiple bits of data. And I will show that. How do we solve this for the entire set? But I do think that, well, I thought when I was solving this and I drew two arrows next to each other and thought about this idea, that it was just really clean how it came out. Now you might think, okay, cool, we can take this, maybe we can abstract this idea into a function and then start looping over things, perhaps. Maybe you're thinking that way. If you've seen Michael Higginson's Dialogue 22 talk, he mentions the idea of programming without loops or making your loops really, really tiny. And indeed, that's the approach we're going to sort of take here, a bit more of an APL way of doing this for all the combinations of connections and sessions that we have. So we have the basic idea. What we want to know now is how are we going to do this when we have many sessions? So we'll use 6 for our example. And we have many connections. Here I'll just look at 4. So to get the basic idea of this, we're just going to start by looking at the session start times and the connection join times. And what we can do, if we just look at these, is say, okay, well, if we have an outer product max between start and join, start is now a list of start times, join is now a list of join times, then we can get a table. And the table is showing for the start time, which is a row, and a end time, which is a particular column, which time is later. And then to get the overall overlaps, we can do a similar thing with the end times and the leave times. And as long as we make sure that these two tables have the same shape, and we do that by putting the session variables, the end and the start, on the left of our outer product so that they correspond to the rows, and the leave and join variables, the connection variables, on the right corresponding to the columns. When these two matrices have the same shape, we can just simply use the minus symbol here, the hyphen, the dash, and APL will do the subtraction element by element across both of these arrays for us. And then we get our overlap times. In particular, you'll note, and this might answer the question in the chat about meetings starting late, if you have a positive number in our overlap matrix, then that indicates that there is some overlap between a session and a connection. And if you have a negative number, then that indicates that the session and connection are completely separate in time. They don't overlap at all. So then for the last part of the problem, as stated here, is we need to compare these overlaps with the duration of each session, and that's just the end minus the start. So that's the duration of each of our 6 sessions here. And we just want to know, well, this is basically the encoding of the problem as stated. Well, we're saying that a person attended a session if they were present at that session for at least half of the duration of the session. And that's literally it, except for this rank error, because we have different rank arrays as arguments to less than or equal to. We have a rank 1 array, a list of session durations, and we have a rank 2 array, a matrix of overlap times. And so we're not able to match those up with less than or equal to directly, like we were able to with the subtraction. Instead, we need some mechanism, some way of pairing up. What we want is to match each individual number, each scalar from our list, with entire rows, each row from our matrix. And indeed, there's a way to do this. It's called the rank operator, because it controls the ranks of subarrays that a function acts on, that it can see. And in this case, we're asking to do less than or equal to between rank 0 subarrays of our left argument, that means the individual scalar numbers, and rank 1 subarrays of our right argument, that's the rows of our matrix. And provided we have the same number of each, which we know we do, then the rank operator will be able to pair these up and then apply our function between. So now we have a Boolean result. You can see here, hopefully clearly enough, that the first connection overlaps at least half of the duration of the second session. And the second connection also overlaps with the second session. The third connection with the third session. And our fourth connection here actually straddles 2 sessions and overlaps both of them by at least half of the duration of their respective durations. And really, that's it. That's all I wanted to show today. This is really the core part of the solution for this problem, and hopefully I've been able to build it up in a way that you could follow and understand relatively easily. But more than that, I think it really beautifully translates from, the concept, the ideas that I've explained using diagrams and talking them through today, translates really nicely onto the actual expression that we end up with to solve the problem. And even the housekeeping about even the housekeeping over rank isn't too much, I hope. And maybe it's not like a big reveal, a bit of a slow burn. Maybe it's anticlimactic. But this is the type of APL, well, that I think really demonstrates the power of the, rank polymorphism is the fancy word, array at a time processing. And then in particular, and this is maybe just my personal preference or the way I feel about APL, instead of taking that expression from before, abstracting that into a function, and then perhaps we could have done our outer product with that entire function or some other way looped over our variables to do the process for all of the sessions and all of the connections. Instead, we do, well, conceptually, I guess it's like a loop. The combinations, we do that in the small, right? We take the individual ends and leaves with an outer product minimum and then end up with a table, and do the same with the starts and the joins. And then we have 2 tables that we can do the rest of our processing on all at once. And that's quite a key idea in array programming, I think. So as I said, that's all I really wanted to talk about today. Of course, this does live as part of a larger solution to the entire problem. I'll follow up with a video where I go through all of the pieces step by step. But to me, the start is just getting the data that we want from the tables and converting that into numbers so that we can actually do this processing with it. And the last part is grouping each of the attendances by the people, because as we saw, some person might join and leave multiple times. But that's, to me, mostly bookkeeping. It really is this part here that I think is the core main part of the algorithm that I wanted to explain. So, thank you very much for watching. One question from Morton is, what if a user watched 30% of a session, lost the connection, then watched the other 40%? Yes, I've sort of hand waved this part away. It really is covered by the grouping part at the end, which I haven't explained because I just take too much time for right now. As I said, that's largely bookkeeping. If the connections are all associated with the same person, you just do an OR. Does that make sense? No, it doesn't. That doesn't answer the question at all. Because that one comparison wouldn't go across. So no, I have to change my solution now. Let me make a note of that for the future. Good, well spotted. You'd have to do a sum, wouldn't you, before you've done all of this? Oh right. So now instead of okay, yeah, let's go forward. I'll say this now, and then I'll fix it in a subsequent video or something. Before we move on, because I've got 5 minutes. So instead of seeing whether the span is less than or equal to this overlap, we'll just take the ratio of the half duration with the overlap. So do divide. And then instead of doing the or reduce, we just add those up. We'll also have to do we'll have to do the comparison anyway. But yeah, that should probably do it.